rational functions and multiplying and dividing rational expressions. So just a reminder, fractions are rational numbers. Rational numbers have an integer in the numerator and an integer in the denominator. We can simplify rational numbers by canceling common factors. We can multiply and divide, and adding and subtracting. Adding and subtracting was the difficult part with the fractions because we had to have common denominators in order to do that. Multiplying and dividing, we don't need the common denominator, so those weren't so bad. So what we're introducing today is the idea of a rational function. Rational function is a fraction where we have a polynomial in the numerator and another polynomial in the denominator. Something like 3x plus 5 over 2x squared subtract 7x plus 1 would be a rational function. And again, we can simplify rational functions by factoring and canceling common factors, just like we did with fractions. We can multiply and divide, which is not too hard because we don't need the common denominator, and then adding and subtracting these, I will warn you, is going to be a bit of work. Okay, so graphing rational functions, a topic we're going to save for college algebra, but we should talk about the domain. A rational expression is undefined if the denominator is 0. You remember we cannot divide by 0. So the domain of a rational function will be all real numbers except for those that make the denominator 0. So what we worry about is the denominator being 0. So some of these you can just get by looking at, but what I like to do is grab the denominator and say I don't want the denominator to be 0. And then I solve, and I get that x cannot be 2. So my domain for this particular rational function is all real numbers except for 2. There we go. So we could write this in interval notation, which would be the interval from negative infinity to 2, union with the interval from 2 to infinity. If I'm using the curve bracket, so that's saying up to 2 but not including 2. Or you can also write it the set of all x such that x is not equal to 2. I'm not too particular which format you use. This next rational function, the denominator is 4, simply a 4. Can 4 ever be 0? No, it can't. And so this one, the domain is all real numbers, which we could write as the interval from negative infinity to infinity. Or we could also write it as all real numbers. Or another abbreviation that's also used for all real numbers is a capital R with a double bar on the R. Okay, this third example here, in the denominator we've got a quadratic. And so what we can do, we don't really worry about the numerator too much when we're talking about the domain. We can factor the denominator, and that looks like it's going to be x subtract 2, x subtract 3. Negative 2 times negative 3 is positive 6. Negative 2x and negative 3x is negative 5x. So again, I don't want 0 in the denominator, so my domain here, x cannot be 2, and it cannot be 3, because those are the values of x that would give us a 0 in the denominator. Simplifying rational expressions, basically factor and cancel. So going back to our old friends, the numbers, fractions, we can factor 25 to 5 times 5, 15 factors to 3 times 5. The formal way of doing this then is that 5 over 5 is equal to 1, and the expression reduces down to 5/3. Most of us are a little lazy and we just cancel out those 5s. But we do have to factor before we can cancel. So this one, we do not want to just cancel the 3y cubes. Let me repeat that. We cannot cancel the 3y cubes. The reason why is in the bottom of the fraction here. That 3y cube is not a factor, it is a term. So we have to factor that denominator, looking for common factors before we can do any reducing. So in the numerator we have 3y cubed. In the denominator we've got a common 3 and a common y cubed. So we can factor out the 3y cubed. That leaves behind a 2y subtract 1. And now this 3y cubed is a factor because it's joined by multiplication. And we can cancel. we'll have to put a 1 up in the numerator as a placeholder, and our reduced expression is 1 over 2y subtract 1. These are a little more complicated, but again, same idea. Factor first, then cancel. If you haven't had enough practice with factoring, you're going to get some more today. So, numerator up here, I think I can probably do these by guessing and checking, as my leading coefficients are 1. Let's see, so x squared probably factor to x times x. And I want to multiply to a negative 6, but add up to a negative 1. So I think a negative 3 and a plus 2 will do that. And then on the denominator, x squared factors to x times x. 8 probably factors to 2 and 4. It could be 1 and 8, but since I want the middle terms to add up to a negative 2, I think a positive 2 and a negative 4 should do that for me. X squared. Subtract 4x plus 2x is negative 2x, and positive 2 times negative 4 is negative 8. And then notice I have a common factor in the numerator and denominator, the x plus 2 and x plus 2, leaving me with a reduced rational expression, x subtract 3 over x subtract 4. So again, what I'm doing is reducing the fraction by finding common factors and then reducing down. This one's going to take a little more work to factor just because I've got some larger leading coefficients. So one technique you might use is working on the side to do some of the factoring and then coming back to your original problem to work the problem out. So coming over here, looking at my 5 and my 1, 5 times 1 is 5. And I'm doing the grouping method, by the way, in case you didn't catch on to that. The way to get 5 would be 1 times 5, but those do not add up to negative 6. Negative 1 and negative 5 multiply to positive 5 and add to negative 6. So expanding my 5x squared to negative 1x, subtract 5x plus 1. I can now do my grouping. Factoring an x out of the first pair leaves me with x times 5x subtract 1. And factoring a negative 1 out of the second pair gives me a positive 5x subtract 1. And this then factors to 5x subtract 1 over x subtract 1. And now that I've got it factored, I can come back to my original problem and rewrite this as 5x subtract 1 and x subtract 1. And again, with some of these that are a little messier, good idea to practice multiplying back at least mentally to double check this is correct. 5x times x is 5x squared. 5x times negative 1 is a negative 5x. Negative 1 times x is a negative 1x, so those would add to the negative 6x. And negative 1 times a negative 1 is a plus 1. And then I've got 3x squared plus 4x subtract 7 to factor. So again, going over on the side here, use a little more room on my screen. Now let's come down here. So 3x squared plus 4x subtract 7. My a times c is negative 21. How about a negative 3 and a positive 7? They multiply to negative 21, but add up to positive 4. So expanding, I've got 3x squared, subtract 3x, plus 7x, subtract 7. Taking a 3x out of the first pair leaves me with x subtract 1. Taking a 7, a positive 7 out of the second pair also gives me an x subtract 1. So this is going to factor to x subtract 1, 3x plus 7. Then taking this factored result back to our original problem, we have x subtract 1, 3x plus 7, and again we're seeing a common factor here of x subtract 1 and x subtract 1, reducing our polynomial rational function down to 5x subtract 1 over 3x plus 7. So quite a bit of factoring goes into these. Everything we've been doing comes back, and we have to keep using it, so you're going to stay in practice. These have a little trick. X plus 5 over x plus under 5 plus x. Addition is commutative, so we can change the order of addition without changing anything in the problem. So I can take my numerator, rewrite it as x plus 5, and then my denominator is x plus 5. These simply cancel out, leaving me with 1. Not 0, but 1. Just like 3 over 3 is 1. This one's a little trickier because subtraction is not commutative, so we cannot just change the order. But what we could do is rewrite it, take the numerator, 5 subtract x, and rewrite it as 5 plus negative 1x. And then I'm going to leave the denominator the same, x subtract 1. So I rewrote the subtraction as an equivalent addition problem. That does let me change the order. And it doesn't look like it helps much, but I'm leading up to something. Trust me on this. What I'm going to do now is in the numerator factor out a negative 1. So negative 1 times positive x would be the negative 1x, and negative 1 times the subtract 5 would equal the plus 5 that I had here. And then this is over the x subtract 5. Now you can see we've got the common factor of x subtract 5, so this reduces down to a negative 1. So if you want to take a little shortcut, looking at the form back here, if you have a rational expression where you have essentially a subtract b in the numerator and b subtract a in the denominator, those will always reduce down to a negative 1.